Greetings to everyone. Next problem, which is related to welded connections. That is, the problem is the circular plate 150 mm in diameter is welded to connect plate by means of 6 mm fillet weld as shown in figure. Calculate the ultimate twisting moment that can be resisted by the weld. Full stop. Use steel of grade Fe410 and sharp welding. So we have to draw the diagram also. So this is the given data with respect to the problem. So here they have around the circular plate, they have made the weld. So this is 150 mm dia. Okay. And this is 6 mm fillet weld. This is the given data. Okay. Now we should move on to the solution. First, twisting moment. T is equal to strength of weld per mm length is multiplied with length of weld multiplied with uh, radius of pipe section or plate. Okay, so first we need to calculate the strength of weld per mm length. Okay, so which is nothing but LW into TE into FU divided by root 3 into gamma MW. Okay, sharp welding, so gamma MW value is 1.25 from table 5 of IS 800. Okay, next one is Fu, they have given as 410 Newton per mm square. Okay, next TE, effective throat thickness. So here 0.7 times of size of weld we have to take. So size of weld, they have mentioned that 6 mm. So 0.7 into 6, 4.2 mm. So next LW. So we are going to do per mm length. So only 1 mm. So which will give PDW is equal to length of weld 1 mm, T is 4.2 and FU is 410 divided by root 3 into 1.25. So if I'm going to substitute these values, I can get 795.36, okay, Newton per mm. Okay, so this is the value we got per mm length. Okay, now let us move on to the length of weld. So total length, here the total length, the formula. So total length means here starts from here to here. What is the total length we are going to do the weld? Okay, so total length to be welded. Okay, so pi d we can put, so that perimeter of the that pipe section we can get it. Okay, circular plate section. So here dia of that circular section is equal to 150 mm. Okay, so if I'm going to use this, I can get pi into d 150 mm. So 471.24 mm. So if I'm going to substitute all this value into this equation, I can get the twisting moment T. So T is equal to 795.36 multiplied with total length of the weld is 471.24 multiplied with the radius of the pipe, that is 150 divided by 2. So if I'm going to substitute all these, I can get 28.11. So T is equal to 28,110,342 Newton mm. So if I'm going to change in kilonewton meter, so T is equal to 28.11 kilonewton meter is the twisting moment. So this is how we have to calculate the twisting moment in the circular plate section. So we'll move on to the next problem. Next problem, problem number 5. A circular penstock, the given data of mild steel 1.2 meter in diameter is fabricated in workshop. So here in fabricated in workshop means shop fabrication, okay, with 12 mm thick plates. The plates are secured by 8 mm size fillet weld. Provided on the inside and outside of the lapped ends. Determine the internal pressure that can be allowed in the penstock. So the given data, sir, the circular penstock is 1.2 meter diameter, is fabricated in workshop with 12 mm thick plates. So 12 by using 12 mm thick plates, they are going to wind up, okay, now, so that they are going to make the 1.2 meter diameter pipe, okay. Mm. So here the 8 mm fillet welds provided on the inside and outside of the lapped ends, which means if they are going to casting like this, okay, inside they have done one weld and outside they have done one weld, so it have the thickness of 8 mm each. 8 mm thick weld, so size of weld S is equal to 8 mm. Okay, so dia of pipe D is equal to 1.2 meter. Okay, next, if the lab determine the internal pressure that can be allowed in the penstock. So we have to find out the internal pressure in the penstock. So let us go for the solution. So how the way we are going to find out the internal pressure, okay now? So internal force causing bursting, which is equal to strength of weld per length. So we are going to equate these two. So first side, okay, that is pressure Pu into D divided by 2, which is equal to the formula used for internal pressure calculating. Okay, now strength of weld per length. Here, strength of weld we know that Lw into Te into Fu divided by root 3 into gamma mw. So they given that sharp weld. Okay, so gamma mw becomes 1.25. And Fu they have given as 410 Newton per mm squared. That is grade of steel. Te effective throat thickness Te is becomes 0.7 times of size of weld. So size of weld they mentioned as 8. So zero point 0.7 into 8. So it is 5.6 mm. So next to that, we need LW. So LW is nothing but length of weld per mm length. So here inside we can have one weld and outside we can have one weld. Okay. So per mm there will be two length. Okay, which means in a single place we can have inside as well as at outside. Okay, so which is nothing but 2 mm. Okay, at a single place inside and outside we can have. So LW is equal to 2 mm. Okay, so we are going to substitute these values. So which is nothing but Pu we don't know. D is nothing but dia of pipe. So D is equal to D. It is equal to dia of pipe. So which is nothing but 1200 divided by 2 is equal to 2 into 5.6 into Fu 410 divided by root 3 into gamma mw 1.25. Now the only unknown is Pu. So we can calculate this. So 3.535 Newton per mm squared is the internal pressures which going to cause because of this pipe section. Okay. So we should move on to the next problem. Next problem 6. Sixth problem we are going to. Sorry for the inconvenience. I'm going to write the problem. Okay. A time member is nothing but tension member. Okay. A time member consisting of an angle section, that is ISA 80 mm by 50 mm by 8 mm. Fe 410 grade steel is welded to a 12 mm thick gusset plate, GUSSET, gusset plate at site. So here it is site fabrication. Okay. So the gamma MW value is going to change. That gamma MW value becomes 1.5 right now. So design welds to transmit load equal to the design strength of the member. So in this problem, they didn't mention about the load. So how much the load is acting, we don't know. So first we have to calculate how much tensile force is going to act on this particular member. Okay. So after calculating that member, load, we have to go for design of welded connections, which is nothing but the length of the weld we have to find out. So this is the two process we are going to do right now. So let us go for the solution. So first of all, I said no, the tensile strength of the section which is going to carry that we have to calculate right now. So what is the formula? Okay, that we are going to share it right now. So from IS 800 2007, the tensile strength. That is the design strength due to yielding of cross section, which is equal to TDG is equal to AG into Fy into gamma m naught. Okay, so whereas gamma m naught is equal to partial safety factor for the failure in tension by yielding. Okay, so see table number 5. So here we are going to use gamma m naught value in table 5. Okay, table 5 gamma m naught yielding. Okay, gamma m naught is equal to 1.10. Okay, so gamma m naught value is equal to 1.10. Now we can go for the solution. So design tensile strength. Design tensile strength of the section. That is TDG at yielding. Okay, at yielding. TDG is equal to AG into Fy by gamma m naught. So gamma m naught is equal to 1.10 from table 5 of IS 800 2007. Now we know the formula, we know the value of Fy. Fy is equal to 250 Newton per mm square. We know that. Okay, now what is the value of Ag that we have to calculate? So Ag for the given section, that is ISA 80 by 50 by 8 mm. Okay, now we have to find out from handbook. Okay, IS handbook. So we'll share the handbook right now. So here is the handbook. Okay, so IS, that is unequal angle. Unequal angle in the sense where web and flange have different length. Okay, so this one is web portion, that is 80 mm. This one is 50 mm. Okay, like that. So ISA 80 by 50 by 8 mm thickness. Okay, now for that, what is the area? So area in centimeter square is equal to 9.78. So in mm squared it is 978 mm squared. Okay, now next is C z z value also we need, which is nothing but centroid of the section. Okay, now that is 2.73 mm. So which is nothing but 27, sorry, 2.73 centimeters, which is nothing but 27.3 centimeters. So let us move on to the problem. So AG value is equal to 9.78 cm square, which is nothing but 978 mm square. And also Z value we need. Okay, CZ is equal to 2.73 centimeter, which is nothing but 27.3 centimeter mm, which is nothing but if I am going to think that this is my gusset plate. In the gusset plate, if I'm going to place the angle like this, okay, where is the centroid lies? Okay, now that is called CZ value. Okay, now so from here to here it is 27.3 mm, and from the top to here it is 80 minus 27.3 mm. So based on that, the force carrying capability, since I'm going to do the weld, okay, I'm going to do the weld in two places. One is here, okay, now at the bottom, and another one is at here at the top, okay. So the size of weld they have mentioned that so we have to find the size of weld also. Okay, now so here there are two plates. One is gusset plate have the thickness of 12 mm. Okay, now and another plate that is the angle section thickness is 8 mm. So based on that, from table number 21 we have to choose the size of weld. Okay, so now let us go for first we should find out the value of design tensile strength. Okay, so TDG is equal to, okay, 978 multiplied with FY 250 divided by gamma m naught 1.1. So the value becomes 978 into 250 divided by 1.1. So triple two triple 2.273 kilonewton is the value of TDG. So design strength, tensile strength carried by the entire section becomes 222.273 kilonewton. Now I need the size of weld. Sorry, length of the weld at bottom as well as at top. Okay, now so here with respect to the center of gravity CG about section. Okay, now so at bottom how the total force has been carried by two sections. Okay, one is at bottom, another one is at top. Okay, now so at bottom how much value it is going to take, how much load it is going to take, that I have to find out. Similarly at top how much load it is going to take it, which means the total load 222.273 is going to divide it into two portions. One is at bottom and another one is at top. So so based on that we are going to find out two different length of weld. Okay, now at bottom we can have separate length of weld and at top we can have separate length of weld based on the nature of force. Okay, that we are going to find out now. So first, load to be carried by the lower or bottom portion, that is below CG, center of gravity portion. Okay, so that one I'm going to take it as a P1. So P1, P2 we are going to, okay. So P1. So P1 is equal to the total load. Uh, so P1 is equal to, how we are going to write it now? So total 222.273, that is total force multiplied with the distance. Okay. So the lower portion, the distance is 27.3. 27.3 divided by 80 mm. So that is the force is going to distribute. So 222.27 into 27.3 divided by 80. 80 is total web length. Okay. So now the force is at bottom side is acting 75.85 kilonewton. So this force is nothing but lower or bottom portion. Okay, now of angular section, of angle section, which is nothing but here how much load is going to act. So 75.85 kilonewton is going to act here. Next, top portion of angle. Normally we are going to place angle like this, okay, but in the given problem, in the figure they have mentioned like this. Okay, now that's why. So in the top portion, so how much? So remaining this distance we are going to set. So this distance, if I'm going to take based on the value, the load is going to acting here. Okay, so which is nothing but P2 is equal to 222.273 into 80 minus 27.3 divided by 80. So 222.27 into 80 minus 27.3 divided by 80. So 146.42 kilonewton is going to act here. 146.42 kilonewton force is going to act here. So corresponding to this force, what is the length of weld we have to give? And corresponding to this load, what is the length of weld we have to give at the bottom? So these things we have to calculate right now. So now I will rub this side, okay? So we all know that the formula length of weld, strength of weld is equal to, so this is the formula we are going to use, okay? So instead of PDW, we are going to use P1. So LW into throat thickness, okay? That first we have to find out size of weld, okay? So size of weld we have to choose from the section. So here 12 mm and 8 mm. There are two thickness. So based on that, the maximum thickness is 12 mm. Okay. So with respect to 12 mm, the size of weld in the IS code book is 5 mm from table number 21. Okay. From table number 21. Okay, from table number 21, the maximum thicker plate is 12 mm, so it is lies between 10 to 20 mm, so that the size of weld becomes 5 mm. Okay, let us go to the problem. So the size of weld S is equal to 5 mm. Therefore, throat thickness T is equal to 0.7 times of 5 mm, which becomes 3.5 mm. So let us consider for P1, that is 75.85 into 10 cube Newton is equal to LW1 into throat thickness is 3.5 mm into FU is 410 root 3 into 1.25. If I am going to substitute this, I can get LW1. Okay, so this is LW1. Okay, so what is the value? So 114.44 mm. Similarly, for the next force, that is with respect to P2, what is the length required that we have to find out now. So with respect to P2 is equal to LW2 into TE into FU divided by root 3 into gamma MW. Okay, so sorry, one thing I forgot. In the given data, they mentioned that site weld, okay, now that is site fabrication. If it is site fabrication, then gamma W value becomes, gamma MW value becomes 1.5. Okay, so here I am going to substitute as 1.5. So 1.5. So the value becomes 137. 137.44 mm. So next LW. So P2 is 146.642 into 10 cube. LW we have to calculate. TE is 3.5 mm. FU is 410 divided by root 3 into gamma MW is 1.5. So 146.42. 265 mm. LW2 is equal to 265 mm. So now we have to draw the diagram. Now we have to draw the diagram. That is, this is our gusset plate and this is our angle section. This is our gusset plate and this is our angle section. So this is our flange portion of 50 mm and this is our web portion of 80 mm and the center of gravity is lies here, 27.3 mm. The red color line is indicating gusset plate. Okay, and the blue line indicating angle. Okay, now the black line is going to indicate weld. Okay, so at the lower portion LW1 is 137 mm. So the length is 137 mm, and the upper portion, that is top, LW2 becomes 265 mm. So this is our final result.